In this video, we're going to discuss the relation between the time domain and the frequency domain. If we have a signal that is sinusoidal, so I draw it here, not a nice sign, but let's say that it is one perfect sine with a single wavelength. Then if we make a Fourier transform of the signal, we get a distinct frequency. If there's some modulation, as I've shown here, in fact a non-ideal sinusoidal wave, then we get some broadening, let's say, of the peaks. And this is also the way the frequency modulation in radio signals works. So there's a variation in the time domain, and that causes some broadening of the peak. That means that not there is a single frequency here, but there are more frequencies that are close to that single frequency. Now, if we take another signal, for example, just a square wave, which is 0, then get some value, and then goes back to 0. Of course, a lot of you have seen the relation between the time signals and the frequency signals. And that means that here, say if you do it correctly, you get a sinc function in which, let's say, the wavelength spectrum is limited and goes to 0. Now, since this width has a relation to the width in the frequency spectrum, this, if we increase the width here, that means that we add time, then we also have to add to decrease the frequencies. So that means that the frequency here span becomes smaller. Now we're going to explore that in somewhat more detail within Mathematica. First thing what we have to do is to define the function. And that's a function of time and some variable which we call d as the variable that we use for the width of our square pulse. We have that to define as a precise function that is 0 for values of t smaller than minus d over 2, and 1 for values between minus d over 2 and d over 2, and again 0 for values larger than d over 2. So here we have the precise function. Of this function, we can calculate the Fourier transform. The Fourier transform is a function g as a function of omega, and of course the same variable d, and is the Fourier transform of f van t, d. We have to transform the variable t into the variable omega like this. The result is given by Mathematica. We're going to draw this function, and then we use d as a plot parameter. So this is the manipulation of the plot f of t within the range -3 to 3, and we also define the plot range in the vertical direction. We plot the function g and omega between -15 and 15, and also the vertical range, the plot range, and the variable parameter d is chosen from 1/4 to 4. And now we're going to calculate that. Okay, and here is the result. Let's make that a little bit larger. Then we can see the results a little bit better. Oh. So what we have here is first d as a parameter, and then we see that we have the square wave. We're increasing d, and what you see is that the Fourier transform, so this is the square wave, here the Fourier transform, the frequency domain, when the time domain gets broader, the frequency domain goes down. Okay, you can also do that automatically, auto-run, and there we see the result. There is a clear relation between the width of the frequency domain and of the time domain.